Well, thank you very much, Richard. Good evening, everyone. Thank you very much for staying. I appreciate it's been a very long but fascinating day, and I will certainly whiz through my 127 slides so that it doesn't keep you from dinner for much longer. Yes, so my title of my talk is A Model of Accelerated Aging and Black Sky Research. Well, I'm a physiologist, so you're not going to hear me talking about patients. You're not going to hear me talking about drugs. In fact, my long-term collaborator, Norman Lazarus, with whom I've been working on ageing research for many years, had a background in the pharmaceutical industry. He's now converting himself to being a physiologist, so I acknowledge Norman's long-term contributions to the work we've done together. So in the talk about ageing, the biology of ageing, the physiology of ageing, who do we study? What model do we use? We have lots of terms that have been used. Gerontology, geroscience, geriatrics. We talk about longevity, lifespan, health span. These are all different terms. If we use animal models to try and understand biological processes, we can use Drosophila, C. elegans, transgenic mice. They will tell us something about ageing, but how much do they really tell us about human ageing? Of course, it's difficult to study. We live a long time relative to other species, so we have models of accelerated ageing. We can study cells in culture. We have progeria. It's a disease, it's not ageing, but it's a model of ageing. We have critical illness. And the topic of this talk is microgravity, spaceflight. So we could actually put a big sign up in space next to the International Space Station, indicating that this is perhaps a model of accelerated aging. So of course the International Space Station is a fantastic achievement. It started in 1998, it's hopefully going to go on until 2028. It's in low Earth orbit, about 250 miles above the Earth. It spins around at a great speed, about 15.5 orbits per day. It houses 6 astronauts at a time. And straight away, we've had a conference about big data. When you have n equals 6, you know you've got a problem in terms of your statistical power for any conclusions you're going to draw. And of course, it's a fantastic scientific resource, a laboratory for experiments in biology, human physiology, physics, astronomy, meteorology, and so on. So for the human, it's a physically challenging environment. It can be great fun, but it's a physically challenging environment because we've taken away the fundamental premise of evolving on this planet, which is we've evolved, and every species on this planet has evolved experiencing 1G. That's what we've taken away. To microgravity. So multiple physiological systems are affected badly by microgravity. We could talk about the cardiovascular system. I'm going to show you data about our cardiorespiratory fitness, or VO2 max. The vestibular system, the skeletal system, bones, bone mineral density is lost. The immune system becomes poorer. Our skeletal muscle becomes smaller, becomes weaker. That's my own particular bias. So this all sounds a bit like it's an aging process. But is it? Let's talk about skeletal muscle. It's my particular interest. There's a picture of Garan. He actually came in this lecture theatre a few years ago and gave a talk. He looked a lot better than he does in that picture, having just spent 6 months on the International Space Station. And for those that were at medical school and may remember their force velocity curves for skeletal muscle, what's happened is his muscles got smaller and weaker. He's gone from the blue to the red curve. Well, that is also what happens in ageing. So it's not really beyond the bounds of possibility to say, well, these are very similar processes. But are they the same? If we take a look inside the older muscle, and this is a typical sedentary older muscle, this is an MRI image taken from the mid-thigh region of a healthy 31-year-old female, this is an 85-year-old female, and just by looking at that image you can see what the problem is. You've got less contractile mass, which is the dark grey matter. You've got more subcutaneous fat, but you've also got infiltration of fat and connective tissue. You've got lower muscle mass, that's why weakness occurs, but you've got less muscle mass, and you've got less quality of that tissue. All not good. What is the cause of that? Well, of course, there are multiple factors associated with this sarcopenic process in muscle. One of them is this concept that we are, as we get older, in this chronic low-grade inflammatory state. So-called inflammaging. This has bad things for muscle. So I'll give you 2 examples, IL-6 and TNF-alpha, being elevated in a population of so-called healthy but sedentary older individuals compared to the young. But that leads us on to, well, who are we studying in ageing research to draw conclusions about the physiology of healthy human ageing? Those of you who may remember the royal family, and this individual who used to spend most of his time watching TV, drinking Guinness, smoking, being unpleasant to his family, argued that's not a biological model in whom we can understand the features of healthy human ageing. At the other end of the continuum, and a much smaller fraction of society, you have people who in later life are still competitive athletes. Most people sit, of course, on this continuum. Most studies of ageing, because we're all concerned about frailty and ill health, tend to focus in this direction. But if you want to understand the biological processes of ageing, as opposed to treating it as a disease or a clinical condition, then we've got a problem, because inactivity is really bad for you throughout the life course. We know that when you have to look at type 2 diabetes and its emergence in young children. This is a lifestyle-related disease. So inactivity confounds our interpretation of ageing. So we should put health warnings on studies of ageing if you want to understand biological processes. So let's go back to space. This is John Glenn. He was the first American to orbit the Earth, part of the Mercury program. He did that when he was 42 years of age. Quite an amazing achievement, of course, in its own right. But even more remarkable was in 1998, when he was aged 77, as part of STS-95, the Discovery mission, as part of the shuttle program. He spent 8 days in space. So the question arose, well, how come an individual 77 years of age withstand the physical and the physiological challenges of being in space? And of course, there's lots of reasons. One, he was a senator. That might have helped. The other reason, of course, which is not well known, is the remarkable physiological condition that individual was in. He was not, by any means, a typical 77-year-old. And that's kind of a running theme of the presentation. So what's new about this kind of thinking about how we should approach ageing? Well, if you go back to Hippocrates, he said, that which is used develops, and that which is not used wastes away. If there is any deficiency in food or exercise, the body will fall sick. We could put that in front of the NHS website. Who is going to disagree with that? 400 BC. A little bit more recently, colleagues at University College London, a very famous physiologist, used to say this to his medical students, and we still don't learn this lesson. Exercise is not a mere variant of the condition of rest. It is the essence of the machine. Frank Booth more recently, our genes evolved with the expectation of requiring a certain threshold of physical activity. We are designed to exercise. We are designed to move. The fact that society allows us not to do it is not the issue as far as our physiology is concerned. So we need to have this basic premise. Being physically active and eating well, not smoking, is the default position for maintaining good physiological function across the life course. So we need to apply that to studies of ageing. Otherwise we're contaminating and conflating different issues. So Norman and I came up with this idea of an extrapolation of set points. We have lots of it in physiology, our blood pressure, our pH, our core temperature and so on. So how much exercise do you need to do to age optimally, to not be contaminated? Of course, that's the killer question. We don't know the full answer to that. But hypothetically, this is where you should be, in the green zone. At this point, you're doing enough. Your health span is optimized. You're going to compress morbidity in later life. Now, most people, unfortunately, are in this zone, the red zone, insufficient activity. You've now got health span which is compromised, an uncertain health trajectory, non-optimal aging, and a likely much more extended period of morbidity. We've also included a gold zone. What if you're a master athlete, doing even more than you need to do? Well, the hypothesis here says, well, you're not going to age any better. You may well be capable of more athletic performances, but you're already aging optimally in the green zone. So, let's get some people who are in the green zone. But I told you I don't know where it is exactly. So what we'll do is we'll take people who are comfortably in it. So we did a large study, a deep physiological phenotyping of a group of master cyclists. They were lifelong exercises, aged between 55 and 79 years of age, and we had some strict entry criteria. They had to be able to cycle 100 kilometres in under 6.5 hours as a male. That's a lot. Okay, that's a lot of exercise. So we're comfortably in the green zone, more towards the gold zone. Okay, so you can see what the training distances were. So these were lifelong exercises, non-smokers. We did a deep phenotyping of them physiologically, so I'm not going to have time obviously to show you the data, but I'll show you one set of data, which is their VO2 max. This is their cardiorespiratory fitness, how much oxygen they can consume during whole body exercise. And this is the best marker of your all-cause mortality. The fitter you are, the less likely you are to die. So this is in litres per minute. You can see the males in the triangles here. You can see the females here. So, well, that goes down with age. What's novel about this finding? What's novel about this finding is that we can conclude, because the model we have used has eliminated inactivity, that that's an aging effect. Now, what we're going to do is do what we should do, which is normalise that to body mass. So if you're looking at Mo Farah, he has a VO2 max of around 85 mils per kilo up here. So you can see it's still going down, the males and females have come closer together. Now let's put in a meta-analysis slope for a sedentary male population. That's where it sits. Down and to the left. So that's for fun. So let's take an 80-year-old cyclist and see where they hit the sedentary curve. That's a 35-year functional advantage of the cyclist over the sedentary. But I'm going to turn that around and say that's not a 35-year functional advantage. That's a 35-year functional disadvantage for the young. It's not the old that are exceptional, it's the young that are particularly poor when they're sedentary. Because the older exercisers are following the trajectory of change they should have because they're maintaining what has been given to them by their evolutionary biology. So, let's go back to space. What's NASA's secret pill that they're giving to the astronauts? I've already said it's a really bad environment. You're in 6 months of microgravity, floating around. You are in deep, deep trouble. So what's the pill? They've got to have a top secret pill. Oh, it's this. This is what the astronauts are doing. 2 hours every day, they are mandated. It's not an option. You might like to use the gym on the International Space Station with your towering brain. They have to do this. This, interestingly, is high resistance strength training. I'm not calling it weight training, because of course there are no weights in the microgravity environment, surprisingly enough. But that's what they're doing to maintain muscle mass. They're cycling, they're running, a whole variety of exercise regimens. This is Dr. Joan Vernicos, former NASA Director of Life Sciences. This is her book, Sitting Kills, Moving Heals. They understood many years ago the requirements of astronaut health were centered around their physiology and how exercises and of course good nutrition were central to that. Now, I've lost a little bit of weight over the past few years since I've been at King's. But you can see that, and I like to show these two individuals together because they're doing exactly the same thing. To maintain their muscle mass and function, they're performing high resistance strength training. She's lifting about 4 kilos in the study we performed. He's lifting a couple of hundred. Doesn't matter, the same relative intensity is the important thing. And the gain she's looking for is to not to have a physique that looks like that, but to be able to perform simple functional tasks, getting out of a chair, climbing onto a bus, and so on and so forth. So in fact, we had an editorial recently just about this. This is the frontline treatment for frailty. Many older people are not having poor physiological function because they are old. It's because they are old and deconditioned. So if we go back to the muscles of our master cyclists, this is a series of muscle biopsy samples. If you took that to a histopathologist, they'd say, well, that's a nice young muscle biopsy you've got there. Nice round polyhedral muscle cells. All looks absolutely fine. Nothing like the muscle I described earlier for a typical older person with swathes of fat, small fibres, angulated fibres. The whole thing looks a mess. There's nothing wrong with that muscle. And indeed, if we take the master cyclist MRI scan through the thigh, that's not a sarcopenic muscle. So we're not just talking about an aging process, we're talking about an aging interacting with disuse processes causing that effect. So I come back to the one marker I mentioned. It's all about inflammation and inflammation. These are now the master cyclists in red, the two pro-inflammatory markers that we've measured. They are not inflamed. So when we talk about inflammation being aging phenomena, it's not just about your chronological age, it's about how that aging process has interacted with inactivity to give you a worse off phenotype. There is no guarantee that you're going to be inflamed just because you're old. So, not much just my words, this is Dame Sally Davies. If physical activity were a drug, we'd be talking about it as a miracle cure. Of course, there's lots of reasons why people don't want to do physical exercise. But its potency is dramatic. Can I just ask the audience, how many people are aware of the governing guidelines, or the Chief Medical Officer's guidelines for physical activity? Who knows what they are?
30 minutes a day.
150 minutes of moderate activity twice per week, or 75 minutes of intense exercise, or intensive per week, plus 2 sessions of muscle strengthening exercise. Who here adheres to anything like that? Some of you, which is good, but not everybody. At a conference about ageing, when we're talking about how we're helping older people, we are the next tranche of older people. What are we doing now to prevent us being the problem in 20 or 30 years' time? And the key feature is your lifestyle. Physical exercise, good nutrition, all the other things that, of course, come with that. Not smoking, of course, is another key one. So some closing thoughts from a physiologist. I don't view ageing as a disease. I'm not looking to cure it. We must be careful in our terminology as regards ageing research, and interpretation of the models that we use. If we're studying ageing, then the models that I've shown, I believe, are studying the ageing process. If we're looking to help an older, sarcopenic, frail person, that is not the same question as we're asking about the biology of human aging. That's a different question. The International Space Station is a fantastic resource. We can learn much about human biology in its really unique environmental conditions. It tells us something about aging, but it's mostly telling us actually about a trajectory towards frailty and some model of disuse and unloading. A significant portion of what we see in the diminished physiology of the majority of older people, as I said, is interaction of aging and inactivity and disease-related processes. But the countermeasures in the International Space Station are the same as the countermeasures we have on Earth, which is good nutrition and being as physically active as possible. Thank you very much.